Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on Java native interface and look at an article from IBM about best practices for using the Java native interface, or JNI. And it says techniques and tools for averting the 10 most common JNI programming mistakes. And obviously on the left side I have all my lectures on the Java native interface, and as I walk you through this article about best practices for JNI, I'll point you to the PowerPoint, the slides that I have, or the lectures that when I discuss those practices, right, those points. So 10 most common JNI programming mistakes to avoid by Michael Dawson. And you see this article is relatively old, it's from 2009. And as I mentioned many times during my lectures on JNI, nobody really touches the JNI part of the JDK. People just fork the original repository from OpenJDK and they never touch the JNI. So really JNI hasn't really evolved that much since 2000, I don't know, 5, 6. And it's still compatible with C. It's not compatible with C++, and that's a shame. I think if the JDK developers could put some effort into the JNI to make it fully compatible with C++ and implement it in a more object-oriented way, such that we can pass Java objects directly as a C++ objects or vice versa. That would have been very nice. But for now, JNI is just the same, and nobody touches that. So, so even an article from 2009 is good to look at. All right. So the Java environment and language are safe and efficient for application development. However, some applications need to perform tasks that go beyond what can be done from within a pure Java program, such as integrate with existing legacy code to avoid a rewrite. For example, if you have a very large native code base, you don't want to spend lots of time and converting them to pure Java code. So you just want to somehow interact from Java to that legacy code which is native. Implement functionality missing in available class libraries. For example, you might need Internet Control Message Protocol, ICMP functionality if you are implementing ping in the Java language, but the base class libraries don't provide it. All right. Integrate with code that's best written in C, C++, and this is usually the main attraction of JNI, because we have a large native code, especially for scientific computing. For example, GNU scientific library, it's a massive scientific library written in C, and we don't want to rewrite all of this in Java. That just doesn't make sense. So what we do, we quickly write a few Java and native methods that pass the data from Java to C++ and then grab the result back and bring it back to Java to exploit the performance or other environment specific system characteristics. And regarding the performance, Java has JIT compilation, right? So after a while of running your your Java code, basically the JIT compiler can kick in and optimize your code. So however, as I mentioned in my lectures about JNI, once we have a native code and create the dynamic library by using GCC-03 fast, or basically the highest optimization level, really JIT compiler can never reach that level of performance of optimization that the GCC-03 provides, right? So having a dynamic library that is compiled with GCC-03 is definitely a plus. Address special circumstances that require non-Java code. For example, implementation of core class libraries might require cross-package calls, or the need to bypass other Java security checks, right? The JNI lets you accomplish these tasks. It provides a clean separation between the execution of Java code and native code, such as C++, by defining a clear API for communicating between the two. For the most part, it avoids direct memory reference by native code into the JVM. ensuring that natives can be written once and work across different JVM implementations or versions. And we said that the way this does is it loads dynamic libraries on the fly, so you can never load a static library during your execution of the program, right? During the runtime of your program, you can never load a static library, right? You can build your JDK by linking to a static library, but nobody does that. So the only option is that at runtime you can only load dynamic libraries, right? With JNI, native code is free to interact with Java objects, get and set field values, and invoke methods without many of the constraints that apply to the same functions in Java code. And I said this many times that, especially for example, accessing the fields or methods or let's go here. We said that the process is very similar to Java reflection. However, in Java you have lots of exceptions and there are quite some restrictions. If you want to access a private field, you have to set its visibility, set visible to true. However, in C++ there is no such thing, so JVM doesn't have any checks because there is no compiler. Remember, all these exceptions are compile time exceptions or check exceptions that you have to deal with. Similarly, for accessibility rules, for example, accessing a private field, it's a compile time or maybe a runtime, I'm not sure, but in C++ there is no Java compiler, right? There is no Java C. So the assumption here is that everything happens at runtime. Therefore, JNI JVM can't have any strict control on the checked exceptions or whatever, right? So basically, the bottom line is that when we're using JNI and writing native code and accessing Java objects, it's a direct access or unrestricted access to the Java heap or meta space. Meta space. I believe in JDK 7 or below that it was called permgen, but then it was renamed to meta space. So set field and invoke methods without many of the constraints that apply to the same functions in Java code. This freedom is a double-edged sword. It trades the safety of the Java language for the ability to accomplish the tasks listed earlier. Using JNI within your application provides powerful low-level access to the machine resources, memory, I/O, and so on. And we've seen a couple of examples. For example, resources. I think when I talked managing native resources, we discussed how this works. We have a private static native init IDs that initialize the IDs of the methods or the fields that we want, and then we have to implement the auto closable because we're managing a native resource, and then we have an open 0 and close 0. So this is a tradition or a convention that we always follow. These are private native ones, and then auto closable has a close method which is public, and in the close from this auto closable typically we call close 0, which is a private native. And for safety, we can also override the finalize and call the close 0 to make sure that the native resource is cleaned up and closed. And we also discussed a standard I/O. We said that the way this works is that we can have init IDs, and whatever we, for example, for console in, when we say next to get the next word, we just create a std string, and then from std cin, which is automatically open by default. Remember, the standard IO, std cin and std cin are open by default. As soon as your native application is run, the operating system allocates resources, or basically, and part of those resources are the input output channels, and also std error, the error channel, right? So operating system has to allocate these resources to the console applications that are natively running. And when I implemented this, I showed you that if I want to get a string from the console, all I have to do, I have to, in the native code, create a std string and then say std cin and then use the insertion operator, and it reads a word, puts it in the std string, and then we say jvm new string utf, and then get the character array of that std string. So it's very standard and very straightforward way. And if you don't recall, you can go and watch my in-depth lectures on working with a standard IO. Obviously, we don't need to do that because Java already provides a system.in and system.out, and these are byte streams that are natively implemented. As soon as the JVM launches, it initializes these basically streams or channels, and these are hooked up to whatever underlying native streams are in the operating system. And when we, in terms of memory, we discussed, for example, a couple of examples. One was how to map the C++ objects to Java objects. So let me see if I can find it. Anonymous classes, creating, or for example, creating unsafe class. And this was for accessing or allocating memory off heap, right? And we said that it was very easy, and all we have to keep track of is the address. It's a 64-bit integer, right? So it was very easy to implement it, and we said that JDK also has SunMISC unsafe, and it's going to be highly encapsulated in the JDK because of the after Java 9 and the JDK was modularized. There's going to be a strong encapsulation, and I think the normal developer won't be able to easily access this unsafe class anymore. But you can always follow my lectures and write your own unsafe class, right? So you're working without the safety net usually provided to Java developers. JNI's flexibility and power introduce the risk of programming practices that can lead to poor performance, bugs, and even program crashes. And even you've seen through my lectures that sometimes I just deliberately crash the JVM. So it's very easy to crash the JVM. For example, you pass some object pointer to a function that expects some primitive types. Any error that happens, I mean, if you're writing Java code, obviously an exception will happen. However, when you're interacting with JVM in the native code, usually just JVM crashes, right? Bugs and even program crashes. You must be careful about the code you include in your application and use good practices to safeguard the application's overall integrity. This article covers 10 most common coding and design errors that users of the JNI make. The goal is to help you recognize and steer clear of them so that you can write safe, effective JNI code that performs well from the start. This article also introduces available tools and techniques for finding these issues in new or existing code and show how to apply them effectively. JNI programming pitfalls fall into two categories. One is the performance, second is the correctness. Performance: the code performs the designed function but does so slowly or in a way that causes the overall program to slow down. And we said that one of the problems of going from Java to native and coming back is the garbage collector. JVM has to create a safeguard for garbage collector before transitioning to the Java code, and that safeguard and maybe some locking on some objects or whatever causes some slowdown in calling native calls. Correctness: the code works some of the time but does not reliably provide the required function. For example, you might have to deal with some raw memory in C++ and you have to do some memory management manually. In the worst case, it crashes or hangs. All right, so let's also look at this column, JNI's evolution. We've already looked at the Oracle's documentation, which described how the JNI came to be from JDK 1.1 onward. So JNI has been part of the Java platform since the JDK 1.1 release and was extended in the JDK 1.2 release. The JDK 1.0 release included an earlier native method interface that lacked clean separation between native and Java code. In this interface, natives would reach directly into JVM structures and so could not be portable across JVM implementations, platforms, or even versions of the JDK. Upgrading an application with a substantial number of natives using the JDK 1.0 model was expensive, as was developing natives that could run with multiple JVM implementations. The introduction of JNI in the JDK 1.1 release allowed version independent, platform independence, and VM independence development of third-party class libraries. It is interesting to note that younger languages such as PHP are still struggling with these issues with respect to their support of native code. And obviously PHP is not at the top anymore. So, I mean, this article is from 2009. So, performance pitfalls. The top 5 performance pitfalls for programmers using JNI are not caching method IDs, field IDs, and classes. And we discussed in details about this. Triggering array copies, we discussed in a huge depth in our lectures. We said that we have to go, we shouldn't send object arrays to native code. We have to avoid that as much as we can, only send primitive arrays. And when we go to the native code, we shouldn't use get, for example, double array region or anything. We have to access the primitive arrays critically so that the JVM doesn't create a copy behind the scenes. Reaching back instead of passing parameters. Yeah, this is also another pitfall. We discussed this. Choosing the wrong boundary between native and Java code. Using many local references without informing the JVM. And we discussed this when we discussed, when we looked at Oracle documentation. And we said that if we have a for loop, we are iterating over an array of objects. Remember, objects in the native code, then JVM has to create local references for those objects, and that causes problem. And JVM has an upper bound or a default limit on how many local references it can handle in a native call. So if we think that we probably need more than that, then we need to inform JVM. It has a method to actually set the limit on the number of local references that it can create. Because remember, the more local references you create, after you go back, somehow those references should be cleaned up, right? Which means more work for garbage collector. All right, so the first one is not caching method IDs, field IDs, and classes. So let's go with caching field IDs here in C++. We take the following steps for instance and static fields. We find, first of all, we have to get the hold of the J class so that we can talk to the JVM, right? Remember, J class is our entry point of talking to the JVM, because JVM needs to know which class we're talking about. And we usually get the J class by locating it on the class path. I mean, the class has to be on the class path. Obviously, in native code, there is no Java compiler checking, right? So if the class is not on the class path at runtime, we get a class not def error or class not found error or something like that. So we find a class, get a JClass handle, and then field ID if we want to access a field. Field ID is just memory offset within the class Java object so that JVM knows at what offset to the JClass address it has to locate this this field, right? The identity of the field. Get field ID or get a static field ID. We pass the JClass, the name of the field, and the signature. And then we said that there are two approaches for caching. One is method caching, the other one is global caching. And global caching is much preferred when we have lots of fields in a class that we need to access in native code. So we usually have a private static native init IDs. And in the init IDs, in the implementation in the native code, we cache, or we basically initialize all the field IDs and method IDs that we need to use, right? So we initialize them one, and we put it, and then we put that init IDs inside the static initializer. And let me see if I have. So here I have the method caching, and if we declare a variable in a function as a static variable and we immediately initialize it, next time the function is called, this variable is not going to be initialized. So what this means is that it's going to hold its previous values, and we can use this approach to initialize field IDs. But then if we have multiple native methods, then we have to initialize them each time. So that might cause some overhead, but if we globally initialize them inside the init IDs implementation, then we only initialize once. Yeah. Not caching method IDs, field IDs, and classes. To access Java objects, fields, and invoke their methods, native code must make calls to find class, right? To get find the class on the class path, and then gives us a JClass handle, so that that's our entry point for talking to the JVM. Get field ID or get a static field ID, right? Get method ID, get a static method ID. In the case of get field ID, get method ID, and get a static method ID. We can also have a static field, right? So get a static field ID. The IDs returned for a given class don't change for the lifetime of the JVM process, right? These are just offset within the memory offsets within the JClass struct, which is the internal representation of the Java object in the Java heap, right? And then that the value of that field is at that offset, right? So we need to know this offset only once, because we're not dynamically changing the class structure at runtime. But the call to the get field or method can require significant work in the JVM, because it has to do a lookup, right? And lookup is more or less linear search, so it's going to take some time. So it's always best to cache these. But the call to the get field or method can require significant work in the JVM, because fields and methods might have been inherited from superclasses, making the JVM walk up the class hierarchy to find them. Because the IDs are the same for a given class, you should look them up once and then reuse them. Similarly, looking up class objects can be expensive, so they should be cached as well. All these J classes, they're the same, right? So, I mean, there is a caveat here. We said that if you're creating new objects, JVM arrow new object, you shouldn't cache that class, JClass. That was the exception, and I discussed this in depth in one of my lectures, so you can go back and review them. For example, listing 1 shows the JNI code required to call a static method. So J method ID, so we define this globally, and then or locally, doesn't matter. If it's local, we define them as a static. If it's global, we just we can also define them as a static, so that the linker doesn't see them outside the CPP file. We get the class, find class on the class path, and then exception check. It doesn't matter. I mean, we typically are sure that no exception happens. We assume that this class is available on the class path. And then we get a method ID, get a static method ID, JClass, the name of the method, and the signature, which is the signature of the parameters in round brackets, and then the return type. And again, if this signature doesn't, JVM can't find this, it can throw exceptions, doesn't matter. And then get a static void method, and we said that in order to call the methods, calling the method in C++ or calling the static method, this it depends on the return type, right? And the functions inside the JNI are specialized for the primitive return types. For example, if I want to call a method that returns a void, I say call a static void method for a static method. If I want to call a method that returns a primitive type of type integer, I say call a static int method. But if the return type is anything but a primitive, so if it's an object, Java object, we say call a static object method, which means it's a static method, we're calling it, and it's going to return an Java object, right? Looking up these class and method ID every time we want to call the method results in 6 native calls instead of the 2 that would be required if we had cached the class and method ID the first time they were needed. Caching makes a significant impact on your application's runtime. Consider the following 2 versions of a method which end up doing the same thing. The version in listing 2 uses cached field IDs. So the way we cache them, so get field ID, return these. Listing 3 doesn't use cache. So this uses the cache one. This one, each time this method is called, this function is called, it looks up the IDs, which is time consuming, right? The version in listing 2 takes 3,572 milliseconds to run. Listing 3, 86 milliseconds. So this is 20 times slower. So I also had some examples in my lecture, so I encourage you to go back and watch it. This is one of the most important performance tips in using JNI. You have to cache all the field IDs and method IDs, preferably in a global way, Performance tip number 1, lookup and globally cache commonly used classes, field IDs, and method IDs. So this article suggests that always globally cached IDs, but I mean C++ provides a way to cache the fields cache the variables in a method or function using the static keyword. It's not really recommended to do that, so it's always best to use global IDs. But just for the sake of completeness, I mentioned that you can also locally cache these IDs inside the function itself, right? Alright, this was the first one. I hope you enjoyed this lecture. Please stay tuned, and I'll see you in the next one.